All right, our next speaker this afternoon is Giudice, who's joined us from San Francisco State University. Chris has been working with James this summer, and today he'll tell us about his work, empirical constraints on chemical equilibrium timescales in the Milky Way.
Thank you, Gwen. So a lot of you are probably wondering, what is chemical equilibration and why am I studying it? So previous theoretical expectations of chemical evolution in the Milky Way galaxy have shown star formation causes metallicity to increase, or does it? So recent advancements in technology have allowed us to put this to the test by looking at, by comparing age and metallicity relations of stars in the Milky Way. This works because stars in the Milky Way sort of act like a time capsule of information about the ISM when they formed. And so by looking at them, we can find out what the abundances of metals in the ISM looked like when they formed. And this is exactly what my mentor James did when he published his paper back in, or actually it published this year. So this is a figure from that paper. This plot represents his work. The metallicity notation here follows conventional metallicity notation where it's the ratio of metal to hydrogen relative to the sun in a logarithmic relation. The figure on the left represents the oxygen to hydrogen ratio, and the figure on the right represents the iron to hydrogen ratio. Both figures have several trend lines that represent bins for different ages of stars. And you can see that there's no significant difference in metallicity gradients for stars of different ages, with the exception of 9 to 10 gigayear-old stars. If these are real, which we're not sure that they are, we're not sure that they're not just the cause of the way that he looked at the data. If they're real, they're probably just a representation of the galaxy reaching that equilibration or that equilibrium. What is the equilibrium theory? So the theory proposes that the metallicity in the ISM approaches a constant value for different radii. This is a much simpler scenario than previous theories have proposed. This equation is derived from more complex chemical evolution models, and it's the essence of the equilibrium theory. So a tau EQ here, right here, is a variable of note. It represents the speed at which the equilibrium is reached. In this next slide, I will show that equation graphed onto a plot. On the y-axis is metallicity of magnesium, and on the x-axis is stellar age. And so you can see I've plotted two different scenarios, one where there's a short equilibration timescale that is a small tau EQ on the order of about 1 gigayear, and then a long equilibration timescale, which is a tau EQ on the order of about 10 gigayears. The equilibrium scenario is still very new. It was only proposed by James. He finished his paper last year, and so has yet to be put through the ringer. So the goal of my project is to create a model and put it to the test. I'll create a simple model. I'll circumvent full-fledged equilibrium models by parameterizing the equilibrium scenario directly as an asymptotic approach to an end-state metallicity. And so to give more context on what that equilibrium scenario is about, this is sort of a this is sort of just an estimate of what the abundance of magnesium in the galactic plane looks like as a function of galactic radius. This is not actually real data. This is just sort of an estimate. And so what the theory proposes is that this is the equilibrium that the ISM is reaching. So now you may be wondering, what data am I working with? So I'm working with SDSS-5 data. It's roughly 420,000 stars. and it's the first data release of Milky Way Mapper. And it's unprecedented coverage of the galactic plane, and so it provides us with a lot of detail on how chemicals have evolved in the Milky Way. This is what that coverage looks like. So on the x-axis is the galactic radius, and on the y-axis is z, which is the offset from the galactic plane in this situation. This is in cylindrical coordinates. The lighter colors represent further away stars, and the darker colors represent closer stars to the sun. And so you can see the sun is right there, right at the center of sort of where all those lines are coming out of. Due to the luminous nature of red giants, we're specifically focusing on the red giants branch. This is a very new data release and is the most detailed representation of the red giants branch to date. So this is the data I'm working with. But what I really want to focus on is the actual metallicity to star age relation of this data. This is what that looks like. So I've constrained the galactic radius to 7.5 to 8.5 kiloparsecs from the galactic center, and within 0.5 kiloparsecs of the galactic plane. You may notice this little spur here. We believe this is caused by stars migrating from the inner galaxy, really close to the core, and then migrating out towards where the sun lies. So these stars formed in higher metallicity regions and then migrated to lower metallicity regions. The model I'm creating will ideally look something like this. It's an asymptotic approach to an end-state equilibrium. Overall, my goal is to create a model, and a model that accurately recreates the data I'm working with. And so how I created that model was I started with, I randomly sampled birth radius for stars from an exponential distribution with an R star in this equation with 2.5 kiloparsecs. Then I calculated from that an SFR, a star formation rate distribution for each one of those stars, which was based on its radius. And then from that distribution, I randomly sampled an age for each star. To get my abundances, I used the equation that I was mentioned earlier, where the equilibrium Z is calculated based on both the birth radius and the age of the star that I sampled previously. Then I wanted to take into consideration age uncertainties, and so I added a normal distribution with a sigma that's dependent on the age of the star. And then to consider radial migration, I also did a similar thing where I added a normal distribution to the birth radius based on the age with a sigma based on the age of the star, which gave me my final radius. And so what this left me with was a birth radius, a final radius, a magnesium abundance, and an age. And so what I started with was I started by plotting a model comparison to the real data for a long equilibrium timescale. And so this is what that looked like. I did about 9 gigayears, and so you could see it fits the model. I mean, it fits the real data pretty well. The red is the model, and the blue is the actual data. It fits it pretty well, but it's not exactly perfect. And so my next step was to compare it with a short equilibration timescale of about 3 gigayears. And so you can see the difference here is very noticeable. Visually, it's apparent that the fast equilibration timescale is much more favorable to the real data. This is a simple model, though, so of course it's not going to line up perfectly, and due to the simplicity, it's not matching the data perfectly with that spur there. But overall, it's a much better fit. So what this means for galactic evolution is it points towards a vigorous baryon cycle, and so generally the ISM is moving very fast. So that's my work so far. Thank you.
So I was wondering, it seems like, yeah, the main effect of the faster equilibration is that it kind of, the equilibrium ends up being at a higher metallicity.
Mhm.
Do you have a simple explanation why?
Yeah, so it's sort of just basically because it reaches that equilibrium faster. And so in this graph, you could see two representations, a long equilibration timescale and a short equilibration timescale. This is without considering, this is just specifically looking at 8 kiloparsecs and not considering uncertainties. So you could see that the long equilibration timescale just takes much longer to reach the same place the short equilibration timescale takes. And so that's why it's like the short equilibration timescale is just generally higher in metallicity.
Sounds like there's like some maximum metallicity that is
Yeah.
be a thing, but any is just so what, like, why is that? Like, what doesn't it keep going?
It keeps going up to, in this case, it's zero, abundance of zero, because I'm looking specifically at 8 kiloparsecs, modeling it after the sun's galactic radius. And so it would asymptote at the sun's abundance. Yeah.
Really nice stuff. Really cool. So the spur that you see in the real data, that's from, you said, radial migration.
Yeah, that's the current understanding. There still does need to be more research on it, but the current understanding is that it's from radial migration, yes.
Is it possible at all to capture that specific radial migration in your simple models, or would it require more like 3D star particle type?
I think it would require more complex chemical evolution models. It is possible. There are things that me and James have been talking about possibilities for how to get that spur to show up in my mock data. But at the moment, I haven't been able to reproduce it. Mhm.
Question from Luke.
Really interesting. So for this sample of stars, kind of in our local neighborhood, how many are in the top branch, the spur, versus the lower branch? What fraction of stars near us?
I couldn't give you a fraction. I haven't exactly calculated that, but yeah, so sorry about that. I can get back to you though.
All right, let's thank Chris again.